for 300mm technology transfer and ramp of 0.15, 0.13, 0.18 kind of micron processes. And he also had 20 years of extensive experience in the IC industry, in the technology and management and process and testing. So let's welcome Henry Chen.
Good afternoon, ladies. Presentation. And this is the contents of what I'm going to present. First, I'll talk about why. Why is 300mm? What are the driving forces? And then followed by, I'm going to go over the current worldwide 300mm fab status and the common challenges we are all facing. And then next, I'm going to discuss what we learned about today's 300mm tools. And then followed by, do we have particular issues in 300mm fab design? And what's required for 300mm fab automation? Finally, I'll summarize TSMC's current status and see what conclusions we can draw from my talk. So to answer this question, why is 300mm? The key is that every dollar you invested in a 12-inch fab going to produce more output than the same dollar invested in an 8-inch fab. That's the bottom line. The capital productivity, in other words, is the better return on your investment. How about the running cost? This is not only the depreciation, but to add material cost plus the labor cost. So still making sense? Yes, on paper, in theory, it does. We will discuss that later. And also, the Fab 4 automation promised a shorter cycle time, also going to have a lower manpower used, lower facility used, and lower environmental cost. So these all looks attractive. Let's do some estimation. In general, today, the capital investment to build a 12-inch fab is about 1.6 times for that of building an 8-inch fab counterpart. But the wafer size, we know, is 2.25 times between 12 and 8-inch. So use 2.25 divided by 1.6, and then you know your capital productivity is 1.4 times. So that's quite an incentive. Then for the running cost, other than the depreciation, if you add the wafer material and other labor cost, and Sematech has done some calculation and set a target. 1.6 would be the target. We think somewhere between 1.6 and 1.8 are acceptable. All right? So if you use the worst case 1.8 divided by 2.25, actually you get 80% of the die cost to compare a 12-inch wafer with an 8-inch wafer. But the gross die per wafer, depending on the die size, it can be either somewhere between 2.3 to 2.6. Like this morning, Intel's presentation, they quoted the number is 2.5. That's strictly depending on your die size. So you use the best case. So we say the 1.6 divided by 2.6, you get 60%. your die cost benefit. Hey, if you have a way to cut the cost by 20% to 40%, plus other benefits, plus better capital productivity, will you do it? Of course. But is that too good, or is there a catch? Yes, this all depends on this assumption. The assumption here is everything is equal. If the machine productivity and the wafer volume, they are all equal, then this number can be realized. All right, let's revisit the capital investment. Here's the pie chart, illustrates the kind of a cost breakdown between the 200 millimeter fab and a 300 millimeter fab. Say if you invest $1 billion to build a brand new 8-inch fab, it's going to cost you $1.6 billion to build a 12-inch fab. The equipment cost actually is quite similar. If you can sum up your quote from your vendors and those tools add together is less than this number, please let me know. I always wonder how good our purchasing guys are. All right, let's look at, so in general, the tool is probably running about 1.5 to 1.6 for each tool between 12-inch and 8-inch. For the building, this one, 20% of the total $1 billion investment, so that means $200 million will be spent on the building. Here, 15% of that 1.6 billion, this is 240 million. 240 million versus 200 million. If the building size is slightly larger, this actually is not much different. However, I want to point out is this figure. The automation cost in an 8-inch fab, only 3%. That means $30 million. Here, it's going to cost you 6%. That is almost 100 million. 130, then you know automation is the key to your success of a 12-inch fab. All right, let's take this famous or arguable curve. We think 1.58 might be too aggressive, but like I said, 1.6 to 1.8 is acceptable. This is estimated by the International Semiconductor Organization. And when they published this, they probably did not foresee an economic slowdown. So the current 300 millimeter learning actually has been slow. So if you add December, right in front, 2002, that's about right. So today, the ratio is probably around 2.5. So if you add December here, so that means 4 years later, into 2006, we probably will see a kind of the cost ratio falls into that range between 1.6 and 1.8. There is still an assumption. This curve is based on the assumption the fab is running at close to its capacity. But today we all know the 300 millimeter is not running close to its capacity, but the 8-inch, the advanced 8-inch fab pretty much is close to the capacity. So this number also can be slightly higher. So these are all worth to note. Okay, this is the comparison between the utility usage between a 12-inch line versus 8-inch line. This morning, Intel's paper reported this as well. If you compare from power, water, wastewater, and waste air, and the 12 to 8-inch ratio is all between 1.3 and 1.7, much lower than the wafer size ratio 2.25. So everything is favored the 300 millimeter. Also, from the technology roadmap point of view, the conclusion actually here we can draw is the transition to 300 millimeter is imminent and inevitable. Why? Because right now, although the volume production of 0.13 micron technology still produced in 200 millimeter, but everybody is doing production ramp in their new 300 millimeter fab. And all the 90 nanometer technology node currently is being developed on the platform here. So not much difference in terms of equipment set. So if you want to catch the wagon for 90 nanometer, probably 300 millimeter is the way to go. However, 65 nanometer, we have some challenges. It's the tool probably requires some kind of breakthrough here. We have so many unknowns and also limited 300 millimeter experience, also the tool support. For instance, the photo, it's still uncertain, and the material, SOI, well, the large wafer, what's the quality? We don't know yet. Okay, let's look at the current worldwide fab status. Here, I just make a short summary, a brief list here. There is a most updated October issue of solid-state technology. They included more information and a more complete list. So if you have interest, please refer to that article. I just want to point it out. Today, probably more than half, more than 50% of 12-inch fabs has been into production. And one other interesting thing to know is, like a group here is just say for logic products, put on top. For memory, we put at the bottom, and foundry, we put in the middle. For logic type product fab, they all use only copper interconnect. For memory type of product fab, they still prefer aluminum. In the 12-inch fab, for foundry, we have to do both. Itself presents a challenge in control of cross-contamination. All right, and how about the common challenges for all of us? First of all, is the silicon wafer substrate itself. The wafer cost is still quite high. Like a control wafer, the brand new control wafer, it can cost more than 10 times, several $100s, compared to an 8-inch control wafer. How about the wafer spec, the polished, so-called prime wafer? The wafer surface still has higher oxygen precipitate concentration. Therefore, to have a good device fabricated on a denuded zone, we need to put down an epi layer. That also adds cost. The next challenge is always the machine maturity. Right now, I can say it's only reached about 80% of the 8-inch machine's counterpart. Also, the fab automation. We like it to be fully automated, but right now we are running it semi-automated. Also, around roughly 80% can be done in automation. I think this morning somebody said this industry put a lot of efforts in the hardware and process improvement, but the software, and like here, the metrology vendors, their communication, we can control, we can talk to the machine, which is fine. But if we want to extract the measurement data, then that's still some way to go. So the software actually behind the hardware and the process development. So what we learned about these tools, this is a table summarize the key suppliers, at least from what we can see. In each tool category, from photo scanner, track, etcher, workbench, implanter, and also furnace area, RTA, CMP, CVD, PVD, and a couple of ECP, plus some automation stuff, and this the CIM stuff. And you can see at least 2 or 3 major players under each category. At TSMC, we pretty much maintained our dual source strategy until I think our second 12-inch is online, and we will not set a golden set until that time. And then what general trend we observed from these tools? And first one is there's more and more integrated solutions we've seen from the 300 millimeter tools, like the stacked film. We're trying to put all the chambers clustered together, or in the future is also like a stacked gate structure, like you have the clean station, then you have the gate dielectric growth, and then poly deck, all integrated together. So there's a great amount of this kind of local integration going on. And because of these new features added and lack of experience in the customer side, also in the field, so the vendors need to provide more on-site service support to us. And then in the meantime, we formed a lot of joint development projects between us and the key suppliers. So as a result, this kind of integration work and this kind of cooperation work, we also see the vendors tend to work, from different categories. They tend to work together, like the clean equipment vendor and the depth vendor. They tend to work closely to form alliance or even see some merge happening. So as a result, it's going to be probably less new players to penetrate this equipment market. For some specific trend for each tool group, what we can see is for litho, the twin stage becomes a must in order to maintain same throughput as the 8-inch scanner. For dry etching, yes, the integration, the all-in-one for dual damascene type of etching is the trend. Plus, we can have the hardware integration. Also, we can have the process integration. So integration seems to become the key. Again, in the diffusing area, the wet bench, the single wafer process preferred for defect control and also for clean efficiency. Furnace, also the mini batch or single wafer is for cycle time reduction and uniformity. Uniformity is always a concern because wafer size is larger. Implanter also, single wafer process is the trend. And then for PVD, CVD, again, integration is the trend. Okay, this illustrates, so the past year, how the productivity, the machine productivity has been improving. Like the litho, certainly made some quantum jumps improvement for twin stage, for software upgrade. And then for etch, it stayed quite depressed. It's due to some limitation in the wet bench. Now, it's a good thing that it showed sign of breakthrough. We believe pretty soon, the coming quarter, the etch going to be within the par of everybody. And then, if this curve continues, we would expect probably within a year, we can reach the kind of 1, which means the 12-inch and 8-inch machine maturity becomes similar. So why there is such a 20% gap right now? To answer that, there are probably 2 points we want to point out. The first one is there's a vast experience in 8-inch tools. There are millions wafers being processed already. So lots of lessons learned from the 8-inch equipment. However, those experiences and best-known methods cannot be, or it's hard, or it's difficult to be copied exactly into the 12-inch design. First of all, the two teams are probably different, 8-inch people, at the equipment side. So the information sharing, it can take some time. Another thing is just really because of the hardware and the software design, you can't just copy it, you have to modify. So this slowed the progress so far. So that counts for that 20% gap. Another main reason is initially, everybody trying to design the 12-inch machine based on this scale-up concept. Everything maintained the same, physics, chemistry maintained the same. But we just blow up the chamber or blow up the tube, 2.25, that magic number. And then add more gas, power also increase accordingly. However, with that kind of design in mind, its performance always not as good as the 8-inch counterpart, in terms of uniformity. So the brand new design is actually needed. So once they modify the design, unfortunately, every new design requires several iterations for it to work out all the necessary bugs they have to work out. So these two main reasons kind of create today's 20% gap. And we believe within a year, the 12-inch equipment can catch up. Okay, is there any particular issues or concerns in 300mm fab design? In TSMC in general, we build a new fab every 2 years. So from the business strategy, business plan to design finish, this process going to take about half a year to 1 year. And then from the fab construction starts to manufacturing or production starts, this is about another 2 years. And this is a cross-section. I believe this morning, Intel's presentation showed you more kind of the intra-bay cross-section, and then also along the main I/O. Bruce mentioned the main difference between 12-inch and 8-inch would be the stalkers, in the middle of the I/O, and all the OHTs running along the ceiling. Those are kind of a main thing you're going to observe, you're going to see. How about something else? Actually, from the floor space point of view, the footprint of each machine is not much different because advanced technologies used in 12-inch so requires more masking layers. That translates slightly more processing tool number. Still, the floor is about the same, and the ceiling height actually is the same. So from all the sub-layers, subsystem point of view, it's also very similar. So what are the key differences other than the automation? If you paid attention, from previous few slides, you will notice the facility. Actually, we are running between like 1.3 or 1.7 times. We need more air, we need more water, we need to treat more the air waste or the wastewater. So all the piping size need to be adjusted accordingly, and also the power used in each machine, because the chamber did get blown up, so you have to fit in more power. So the electric power also, you have to increase its usage. So the utility hierarchy is quite different. And also like the two-stage design for the scanner is much heavier. Scanner is heavier. And also because 90 nanometer and 65 nanometer, those advanced technologies being developed, so the floor strength or the vibration spec is also much stronger. So this wafer slab will be thicker. Okay, so if you designed your dream house as your hobby before, you probably know what the following few slides means. It's kind of put yourself like the fab designer. You're trying to design your own fab. First, it's like you have to determine your operating philosophy. What kind of lot size? It's like 25 wafers per lot or 13 wafers per lot. You have to decide. In the fab scale, you want to run a mini fab, you want to run a gigafab. This all determines your design concept. An automation system, you want OHT or you want like an AGV moving on the floor. And the mini environment, you want the Smith box concept, or you rather kind of close everybody in a spacesuit. So once those philosophies decided, then you can do your floor layout plan. After that, you just, on that two-dimensional plot, you just add your utility, put some numbers in, and then environmental concerns. And then you can start to do your third dimension, the cross-section point of view, and then see what kind of L return and things like that, pretty much. And finally, you add your deionizer and the EM wave isolation, grounding, those considerations put in, and your fab design is done. Once that's done, and then the fab is built, equipment moved in, wafer started running. Picture yourself in the ballroom of a 12-inch fab. What are you going to notice the first? Of course, those, like myself, I first saw the 12-inch fab is in the pilot line in Tainan, of south side of Taiwan. I noticed it's just the huge FOUP, the wafer box. And then also the, those large OHTs running in the I/O is quite a scene. So 200 millimeter versus 300 millimeter, actually the FOUP and those OHT, it's the key difference from the fab operation or manufacturing point of view. I'm going to just describe that in the following slides. This is to illustrate the OHT and like the 200 millimeter fab, they're using the AGV, and the 300 millimeter using this kind of track system has this advanced design like the MRT system. But here, still using the turntable design like the San Francisco cable car. Yeah. All right, this one. And this is filmed in our 300 millimeter pilot line. This shows how the OHT grabs a FOUP from the low port of the machine and then transfer it to the next station. And this one shows how there's a sensor, so it can detect there's any object between the OHT and the low port, and as a safety feature. And why suddenly this kind of automation becomes a must? It's all because the wafer. The wafer, 200 millimeter wafer, the thickness is about 29 mils. For 300 millimeter, it is 31 mil thick. And the wafer weight is about 2.6 times. And then if we add the FOUP weight and all the wafer weight is about 9.1 kilogram, almost 20 pounds. And then for 8-inch, it's only 5 kilograms, so it's about 11 pounds. This is very difficult for operator to handle constantly. So that's why the automation is a must for a 12-inch line, just from the ergo reason. Okay, we can see there's challenges because the wafer cost, the raw material cost is so high, like several $100, even for control wafer. So we better have the traceability for every wafer running in the fab. And also the FOUP is quite heavy. Plus the integration of the tool, we cluster the chambers together. Therefore, requires real-time monitor. So this also presents a challenge. Plus the advanced technology. That means all the process control would be tighter. So with all these challenges also present some opportunities. For instance, we require to run multi-lots in one FOUP, and also requires wafer level tracking and wafer level recipe control. And then from these opportunities, it defined these new features in a 300 millimeter fab. Some of them like contamination control, like APC, like the recipe management. 8-inch fab also has this. But here they are all kind of more enhanced. For instance, like the wafer positioning data is even available. If you give those new features and new projects to a bunch of engineers to tell them, say, hey, go to design, and 6 months later, what are you going to expect to see? Probably quite interesting. So we have to we should not lose our focus. So we set our objectives clearly. All this development work in 300 millimeter manufacturing is trying to achieve the following. We got to have better delivery and cycle time from this kind of planning, scheduling, dispatching. It used to be done by human being. Now we write all those algorithms into the system. So it's not people dependent anymore. And then we put the brand of transfer their knowledge into the system. And then also we want to continue this kind of mini environment, operation environment. So that means the local buffer inside the tool and also all the queue time control needs to be strictly maintained. And plus there's a wafer base, so lots of data. You have to have a leading edge CIM in order to maintain the performance per transaction or the GUI interface. The performance cannot be degraded. Therefore, the state-of-the-art CIM technologies has to be deployed here. And then, of course, finally, the cost should be controlled. The budget should not be overrun. With those objectives in mind, so we construct this architecture. Yeah, like I mentioned before, this is the brand of the CIM. The planning, scheduling, and dispatching now is all written in the system, in the algorithm. And then we can link to the total order management. And that means we can manage our on-time delivery and then analyze our capacity more accurately. And this is the core of the system. What it does mainly is to handle all the transactions, millions transactions, and then pump all the data and information to its subsystems. So with all these transactions processed and data management, what we're trying to achieve is a better quality. That will be the end result. So this is the realization of the above mentioned architecture. So this is the system level. We use the side view, the MES, OS, the core. And then these are the to interface to the total order management and all our customer orders coming in from here. Say if a customer places a super hot run order comes in, and then we will check, say, hey, whether there's a specific request from this customer. Is any split needs to be run, then we would generate electronic run card to handle that. And then after that, we will do some scheduling to see which machine is available and then push other lots around. So the scheduling is done. And then it will send signal, say, hey, grab the starting material from a stocker and then put the FOOP with the wafer into the first tool it needs to be run at. Once that is done, then here it will start to check the recipe and then start to run, and then all the real-time process control features kick in and then take data. So for the SPC control, inline control, and also will be used for end-of-line yield analysis. So this advanced process control almost becomes a standard in 300 millimeter. What that means is any major process step, there will be an outgoing quality control OQC step, and also has an incoming QC step. This could be the previous major steps OQC. But still, we have this and that. Mainly is for metrology or some inspection. The data, if we have to use the data from this incoming IQC, the data needs to be feed forward, and then we call it feed forward system, or if the data has to be fed back, we call it feedback system. And all the data used is trying to refine the recipe. The end result is a tighter distribution from the speed point of view or from like the film thickness uniformity or the CD uniformity point of view. That can be achieved. And then this alarm management system used to be to do with like particle problems. So once this is in place, we can greatly reduce amount of alarms. And then the real-time monitor and the fault detection, this actually going to truly tell us where is our process window. And APC has been mentioned, and these, the recipe management and the equipment constant system, these are trying to prevent the disasters. Because once the vendor worked on the system or the PM has been done, we have to run this to ensure the system is intact. And this is the vision. So a future, the eFab or eFactory. Here is like our customer and our account manager. They can just use the capacity analysis feature from the network and then actually place an order. And then if that's an hot or kind of with a kind of super hot status, that information can be directly sent to the fab, and the information will not be lost. It's real time, can be viewed by the fab manager. And also, like the foundry manager at the customer side also can use this system if they have that capability. And then, so this is kind of trying to look at the fab. It's a kind of virtual fab. You can see the performance. For the engineer, it can access not only our own fab's machine, but also a remote site, like the real-time, the FDC system. It can actually compare what the performance of that remote machine is. Finally, let's take a look at the TSMC current status. This is the appearance of our Fab 12, our first manufacturing 12-inch fab. And this one started like 2 years ago. And in 2 years, it's in production. Actually, 3 years ago, took that back. And then Fab 14, our second one, groundbreaking is about the same time, but because the business slowed down, so we slowed the speed to install machine. And this one just illustrates, we are at a crossover point for both 0.15 micron technology and 0.13 micron technology. The defect density actually performs similar. And this is the pictures taken from the Fab 12. And for cycle time, this morning we heard some discussion about a single wafer does provide advantage to reduce cycle time. And we had data showing if we replace these processing steps with the single wafer or mini batch tools, we can see this kind of cycle time reduction. That means the lot size, how many pieces in one lot. So the conclusion. I would say currently the 300 millimeter is in production. And the future expansion will be on 300 millimeter. Tool productivity will mature in a year. And Fab 4 automation will improve cycle time plus some single wafer processing implemented. Interesting thing also here points out, in the past, the optimized silicon on system on chip, the chip size used to be like a 9 by 9, but because the better defect density can be realized in the future, what that optimized size is, how much more functions can be integrated into a single chip is subject to be observed. And then now I heard a new name called the GigaFab. The GigaFab will definitely reduce die cost, but unfortunately, the initial capital cost is still high. This concludes my talk.